Okay, so now I'm going to walk you through how to do a t-test in R. First, we'll go to the module for week 8. So this is R code. This is a data set. This is a data set. This is a data set. We'll use all three. This is the PowerPoint slides. Just kind of a heads up on this is kind of a longer lecture, so there's a lot to the t-test. We're finally getting to things that you can actually use in your life, and t-test is definitely one of them. So there's a couple of varieties of the t-test. So I just want to make sure that there's just a lot to cover, that's all. And then we'll go back to the attribution recode data set. So this is telling you the stuff to download that I just did. Go ahead and take your time to download it. Okay, so when should you use a t-test? We can use this little diagram, this little figure from the Salkind book. Are you examining the relationships between variables? No. Are you examining the difference between groups on one or more variables? Yes. Are the same participants being tested more than once? We'll do both of these. We'll start out with no. How many groups are you dealing with? 2. So then we've got a t-test for independent samples. So you use the t-test when you want to compare the differences between groups. I think it works best if you've got some kind of an experimental design and you want to, let's say in the control group, you give them a placebo. In the treatment group, you give them some kind of a treatment. And then you test if there's a difference between the two groups. This is exactly when right now they're looking for a cure for COVID-19 or a vaccine or whatever. And they say we're doing randomized controlled trials. If you have one group that gets control, another group that gets some kind of treatment, you compare those two groups using a t-test for independent samples. This is why I say it's used a lot. The only other one that's used more would be if there's more than 2 groups, right? You can imagine right now when they're looking for treatment for COVID-19, you might want to try different doses of a medication, or you might want to try more than one kind of drug and see which effect is greater. Then you would use an ANOVA, which is what we'll talk about next week. So for today, it's just the t-test, 2 groups. How do I know if I use a t-test? If I have 2 variables, one of them is a number, the other one is a categorical variable with only 2 choices, then I use a t-test. So let's say that I've got this. I've got a control group and a treatment group from some little experiment that I did. Here's the scores for each of the people. Let's say it's a reading test or whatever. I want to know to improve reading. So the null hypothesis is that the population mean equals the population mean for both groups. If there's no effective treatment, then in the population, both groups should have the same score. And our alternative is that in sample 1, we're going to have a different mean than we're going to have in sample 2. We choose the level of risk. That would be the type 1 error, 0.05. We choose the appropriate test statistic. That would be the t-test for independent samples. We compute our t. I'll show you how to do that in a second. And then we decide if our t fits within the region of rejection. How do you know that? Well, it's in the back of your Salkind book is one easy way to know it. But you can also just Google t-test critical value. And then, sure, let's go to the National Institutes of whatever. So you see this same thing looks familiar from when we were talking about the z-test. So out in this area would be a rejection region. In here, if your z is in there, you would fail to reject. So if we're going 0.05, this tells you here that you got to divide it by 2. So we go 0.025, which is this one. And then this is our degrees of freedom. Your degrees of freedom is your sample size minus 1. So in this case, I have a sample of 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 6. So I've got a sample size of 60. So I go down here to 60 minus 1 on this column. down to 59, 2.001. So I calculate my t. If my t is bigger than 2.001, I will reject the null. If it's smaller than negative 2.001, I will reject the null. But if it's between -2 and +2, then I fail to reject the null. So how would you do that in R? It's just really simple, right? T-test of treatment, control. Got to give it the name of the data set. So we'll do that real fast in R. So I got to read in my data set. It was this one. Let's see. Oh, well, so this is the way I've set it up is I've set it up as 30 observations of 2 variables. It's still 60. But so I've got treatment, control, 30 people in each group. A t-test is robust at, robust, you don't know what that means. T-test works when you've got at least 35 people in each group. So I might not take this to the bank, this t-test. All right, so then if I run that code, I get this output, which looks like this. All right, so my t is -0.13, my p is 0.89. There's my mean of group 1, there's my mean of group 2. So this is between -2 and 2. This is bigger than 0.05. So I failed to reject the null hypothesis and my treatment didn't work. That's the conclusion, right? Treatment has no effect because the means are statistically the same as each other. The p-value is the probability that the null hypothesis is true. So there's an 89% chance that these two means are equal to each other. We want it to be less than 0.05. So we fail to reject the null or we accept the null. Okay. Now we're going to use this attribution recode data set. This is another example, but it's a different way of doing it that I'll show you how. So attribution recode is an actual nationally representative survey. I collected these data in 2014. This variable religiosity, I've got it reverse coded. So I spelled it the wrong way so that I would know. So higher scores on this variable actually mean that you're less religious. Lower scores mean that you're more religious. And this is just things like how often do you go to church? How often do you study your scriptures? Do you believe in God? Do you believe the Bible? Stuff like that. It's really common in sociology to use this religiosity. So we'll read this in so that the data set's in. I've got 1,800 observations on 19 variables. And what I want to know is, in this case, I want to know group differences on the religiosity variable, right? So I want to know if women are more religious than men. So I'll show you a different way you can do the code, but I also have to show you this. So I'll show you this again. So remember how D1 is set up like this, treatment, control, and each row has a different observation on that variable, right? Hold on, I gotta pause this real fast. So if you look at this other data set, attribution recode data set, it's set up differently. So let's say that I wanted to do political knowledge, this variable here as my dependent variable, what I wanted to predict differences on. And over here, gender, you have it set up by row, right? So here I have it set up that each row is one person who answered a survey, and they're going to be different genders based on that, right? So I have to use different code. In D1, each column is a different person. Each cell represents a different person. In this one, each row represents a different person, and this cell corresponds with this cell, corresponds with that cell. So I use different code if I'm going to do a t-test like that. Now, I wanted to do religiosity, right? So here's my religiosity score. So this is what I was saying before. If you have something where you've got a number in a column, like religiosity, and then you've got something where you've got a category, which would be gender, and there's only 2 options in this data set for gender, male and female. So if you're doing that, then you know that it's a t-test. But if I wanted to do religiosity by, say, party identification, well, there's more than 2 party identification options in this, so I'd have to use an ANOVA. So that's the idea. So that's why I want you to know how to do the t-test both ways so that you're not stuck. So here the code's simple. T.test, religiosity, predicted by gender, and then I tell it that the data set is D2. And when I run that, I get this output. Sorry. So my T is negative 2.64. Again, my degrees of freedom is, I've got like over 1,500 observations. So if I go back to this critical values table, right, we're in this column here, remember, and we're going to go 1,500. Once you get above 100, your critical value is just plus or minus 1.96 for a t-test. That's why I remember it so easily. For a t-test, a z-test, regression, it's 1.96. So this is less than negative 1.96. My p-value is less than 0.05. So I conclude that the means are not equal to each other, that men and women are significantly different in terms of religiosity. How much different? Well, the scale goes from 0 to 1. So men are 0.65 on that scale as their mean. Females are 0.63. So men are about 0.027 points less religious than women. Less because remember, religiosity is reverse coded in this case. So women are significantly more religious than men, but it's only a tiny bit. It's not a huge difference. But statistically, they're different. Okay, so let's have you practice now. There's this variable in the data set. We'll look at D2 again. There's this variable called structural W right here. This one also goes from 0 to 1. People who score high on this scale, when you say, hey, where does wealth come from in the United States? People who score high on this say, well, it's political influence causes wealth. American system allows rich people to take advantage of the poor, or some people are just luckier than others. They say that's where wealth comes from. People who disagree with those statements would score low on this scale, this structural W. Ooh, we could do materialism too. That could be fun. So go ahead and run the statistical test. Pause the screen. I want to know if men and women are different and where they think wealth comes from in the United States. So the null hypothesis is that men and women, the mean for them in the population is equal in terms of the structural W. The alternative is that the mean for men is different, not equal to the mean for women. We'll use the t-test for independent samples. Our alpha is 0.05. Our critical value is plus or minus 1.96. The value of our t is negative 2.969. The p is 0.00, and so we're going to reject the null hypothesis. And we're going to say that men and women differ in where they think wealth comes from. I'll just run this here real fast. Again, women are higher this time than men. So this means that women are more likely to think that wealth comes from things like political, these sorts of things, right? Women are more likely to agree with these statements than are men. How much? Well, again, it goes from 0 to 1. So 0.029, 0.027, something like that. Not much, but not 0. And that's all we're doing with hypothesis testing. Okay, personal W, go back to this. Personal W, this variable is the same thing. I asked them a whole bunch of questions about where they think wealth comes from. Look at this person scores really low on structural W, but really high on personal W, right? It's a strong Republican. And they think that wealth comes from this stuff, and they don't think that wealth comes from that stuff. This person's almost the opposite, right? In the way that they score. This person's about the same, this Democrat. They think wealth comes from this, but not so much from that. So we want to know if there's gender differences on this variable. So do it again. Get ready to answer the questions. So I'll just run the code here. Okay. So my null hypothesis is that men and women have the same mean score for personal W. My research is that those means are not equal to each other. I'll use a t-test for independent samples. My alpha would be 0.05. My critical value would be plus or minus 1.96. I get a t of 0.94, a p of 0.34. So what do you do with the null? That's right. Fail to reject the null. Because the p-value has to be less than 0.05, and it's not. And this has to be less than negative 1.96 or greater than 1.96. Just for fun, let's just do this with materialism. I want to know if women are more materialistic than men or vice versa. What do you guys think? Who do you think is more materialistic, men, women, or are they equal? Let's find out. Oh, look, there's significant differences. One is significantly more materialistic than the other. Can you see what it is? So first, we'll look at the p-value, less than 0.05. So we know the difference is statistically significant. The t is negative 3.22. So in terms of statistical tests, materialism, there's a larger gender difference in materialism than there is in any of the other variables we've looked at. And we see that women are significantly less materialistic than men. Let's see if there's another variable in here we can mess around with. Proc, fair. Let's do political knowledge just because we can. You think men or women know more about politics? Did I do something wrong in my code? I think that it's this. Oh, then that should work. Okay. Maybe I typed it in wrong. Isn't that weird that this works? Materialism works. But then when I put in, did I spell it wrong? No. But then when I put in political knowledge, suddenly it doesn't work. Weird. Well, I guess we won't find out. Actually, I can do it like this. Don't worry if you, I'll teach you this next time. But I just want to know the answer to my question. There are differences in political knowledge. That's weird. Why are there more? Oh, I see it. Yeah. Okay. I must have done something to mess with this variable. I'm not going to do any more of this because I don't want to confuse you. We're just going to move on. Okay, so now we're going to look at a t-test for dependent means. Sometimes I let my curiosity get away with me. The only difference on this is that you still have two groups, but it's that it's the same people being tested more than once. So it's like a pre-test, post-test scenario. And it's a within persons difference, not a between groups difference. So then you have to use a different kind of t-test. You still have your null hypothesis that the pre-test and post-test, like that the two group means equal each other in the population, and that your alternative is that the sample means don't equal each other. Everything else about it is the same except for how you calculate the t. And this t statistic is calculated by summing up the differences between the two variables. I'll show you. Right, so you're going to go the pre-test score minus the post-test score and then square those differences. So in the case of a paired t-test, I'm just going to read this data in so that you see what it is. You have to have the same person. So in the first one we did, this one here, I have treatment and control, but these cells are different people on these rows. This time what I have is, this is the same person doing the pre-test and the post-test. So you have to have the same people lined up. And if there are missing values, if any of these are missing, you can't do it. So you have to keep it straight what you're doing. The code is very easy. The interpretation is very simple. But you have to keep straight which one you're doing. Otherwise, you're going to get the wrong answer. So the only difference is you just say paired equals true. Right? If you go to the code here, you're just going to go a t-test of the pre-test by the post-test and paired equals true. And then when you get your output, it's not significant in this case. The p is bigger than 0.05. The t is between plus or minus 1.96. So on my paired t-test, I say there's no difference there, right? But if you wanted to know over the course of a semester, say, did somebody do better? Did they learn? You give them a pre-test, you give them a post-test, and then you see, this is how you'd find out. Okay. So before we showed you things that were statistically significant, but effect size is concerned with the question, how large is the difference? And that can be a really important question. For example, you don't want to know, does remdesivir make it so that people, are they statistically just as likely to die of coronavirus as people that don't get remdesivir? You want to know by how much. How much? So if I take this drug that's going to have side effects and such, how much is it going to change things and make things better? So this is why we're more concerned with effect size. I don't want to know that it's a non-zero difference. I want to know exactly how much the difference is. So there's a website that allows you to kind of test that. So we'll look at the, this is the religiosity one, right? And if I go to the website, here it is. Yes, yes. Sometimes he moves his website around. Okay, he hasn't. Good. So all I need to know is the t-value and the degrees of freedom, and then it'll tell me this. Okay. So we're going to go back to, we're going to run the t-test for religiosity and gender. So my t is negative 2.64 with 1562 degrees of freedom. So negative 2.64 degrees of freedom, 1562, compute. And then here it tells me my Cohen's d, and it tells me my effect size. And you say, okay, that's 0.06. What does that mean in terms of an effect size? Well, I go to the lecture notes, and then down here it shows you. One, oh, I see. 2 independent groups. So 0.06 was what I had, I remember. So 0.06 means that it's between here and here, a very small effect size. And 7 points, if it was up to 0.1, it would be 7.7, but it's between those two. So it's like 3.5%. So this means that on average, men are about 3.5% less religious than women. What you want is a huge effect size, right? I'll show you this in the slides. So this is the difference of religiosity. If this green is the histogram of religiosity for women, the black is the religiosity for men. They're not exactly the same, but they're pretty close. That's not a huge difference. What you would like to see is something like this, right? You'd like to see that, okay, in the LSAT, most people get a 150 on the LSAT. But in my group, they're getting a 160. This would be like a whole standard deviation shift, right? So shifting things by a whole standard deviation would be an enormous change, a big change. The equivalent of you probably getting a 150, or you probably getting a 160. Or the difference of if you were going in and you were going to get a 160 normally, then you get a 170, right? Those are the kinds of shifts that people say, okay, that's a large effect. But you can say specifically how much the effect is. So yes, a t-test will tell you that these two means are not equal to each other, but it doesn't tell you how much. But effect size does, and that can be really important because we don't just want to know, are men and women the same in terms of religiosity? We want to know how much are they different in religiosity. So let's look at our materialism one again, and we'll see how much more materialistic men are than women. Right, so 0.318, 0.299. Go back here. So this is, sorry, negative 3.22. Then I go compute. Now I get an effect size of 0.08. It's not that much different either. Right? So what did I say last time? It was 0.06 was in there, right? We're still not to there. It's still just 0.08. It's not even up to that. So, okay, fine. Men are significantly more materialistic than women, but not much. It's tiny, tiny, tiny bit, right? So that's the idea of effect size. I have you calculate this on your homework because I want you to be familiar with the idea, but I don't ever test you on effect size. I just can't teach you the t-test and not teach you how little it matters. So it matters, right? But a t-test matters because it helps you get to effect size, which is much more important. And this stuff all lays the foundation for where we're moving. So I actually use t-tests and publish research. Sometimes people that do research at the university like stuff about like, oh, should we make this change or whatever, they'll report a t-test, and I'm always the first to say, like, why are you reporting a t-test? It matters, but not as much as the effect size. So depending on what you're trying to accomplish, then you're usually better off just reporting the effect size than the statistical significance of the t-test.